human readable language to write programs compiled into bytecode for the Ethereum virtual machine, if that makes any sense. If you've ever used the Java language before, Java uses a Java virtual machine, which basically works on any device, any computer, so you can write your Java code and run it anywhere. Ethereum is similar. You write your smart contract programs, it compiles down to bytecode for the Ethereum virtual machine, and that virtual machine is run on millions of computers across the world that basically validate that your program is working properly and running correctly. So we actually need to compile, and this is the compiler section. And then you've got the deployment section. In order for others to use your smart contracts, you need to deploy or upload them to the Ethereum blockchain. And once they're there, people can access your smart contracts and run them and do other things with that. And then we've got some testing and some other stuff which we won't touch on today. So let's go back to the file section, and let's go ahead and create a new file. Or no, that's for create new workspace. We want, oh yeah, new file. And we're just going to call this ETH Trust Fund. And every Solidity program or a smart contract needs to end with a .sol file, so it knows it's Solidity. And to start, I'm just going to kind of give you an outline of how this contract is going to work. So the contract itself is going to have an owner. Basically, it's an admin role that is able to add new beneficiaries and deposit Ethereum for new beneficiaries. Then we're going to define a beneficiary. We're going to create a function that will be able to add new beneficiaries, another function to check the balance of Ethereum in our smart contract. One cool thing about smart contracts is that they can actually hold Ethereum just like any human with a wallet can. So smart contracts can actually hold Ethereum, send Ethereum, receive Ethereum, and do all kinds of things with Ethereum, as well as other tokens. And then we're going to create a method to check if the beneficiary can withdraw their tokens, and then an actual function for them to withdraw. And if we have any extra time, I'm going to talk a little bit about events and modifiers. So to begin, every smart contract should have a license identifier at the top. For this demonstration, we're going to be unlicensed, but you can do anything from MIT license, BSD license, GPL license, if you're familiar with open source licensing. This is kind of a new thing that they've added. The compiler complains if you don't have this, so it's kind of something you have to put at the top. And then the other thing you also have to have at the top is declare the Solidity version. So today we're going to basically compile with the latest Solidity version, which is 0.8.13. And this tells the compiler which version and which syntax should be allowed in this contract. Next, we want to define the contract. I'm just going to call this ETH Fund. And if you're familiar with JavaScript or C type languages, a contract kind of resembles what other languages would consider a class. So a contract is kind of like a class that lives on the blockchain, and it has its own methods and its own internal state and variables. So the first variable we're going to define is the owner variable, and the owner is going to be of type address. Now, address is a built-in type for Solidity, and it just represents an Ethereum address that you can actually send and receive Ether to. So basically, this address is going to check whether, so in the future, we're going to check whether the address of the wallet accessing this smart contract is the owner in order to basically restrict or allow this person to call these functions or access any sort of privileged functions or variables. So this is where we're going to store the owner's address. Then, just like in other languages with a object-oriented programming, there is the concept of a constructor. So basically, when we deploy this contract, we're creating an instance of this contract, much like creating an instance of an object in JavaScript or Java. So we've got this constructor function, which basically does all of the setup for us. So in the constructor, we're immediately going to set the owner of this contract to the person that deployed this contract. And message.sender is a built-in global variable built into Solidity to basically denote who is running the transaction to access this function at this given time. One reference I want to point everyone to is docs.soliditylang.org. It's basically the full-fledged documentation for the Solidity language. I've opened up this cheat sheet in the browser, and basically this gives a kind of high-level overview of different global variables. So here you can see some of the global variables we have. The one we accessed just now is message.sender. There's other things like message.value. So if someone is sending Ether as part of a transaction, you can actually see how much Ether is being sent. You can see the block number, the timestamp of the transaction that's occurring, all kinds of things. So this is a totally invaluable reference for anybody writing Solidity code. So the first function we've created is this constructor, which sets the owner as the person deploying the contract. I'm also going to set this owner to public. This is basically this tells the Solidity compiler that we want to be able to view this variable from the outside. And another cool thing about Solidity programming is when you create a public variable, once you compile this will actually create a public method that you can call and actually view the value of this variable. So let me go ahead and this is good. So what we're going to do is compile this and run this just to see basically what's going on. Another cool thing about this remix IDE in the browser is that it gives you a test blockchain in the browser, and then a bunch of addresses, and each address has 100 Ether to play around with. So you can do all kinds of testing before actually spending any real money to deploy your contract. So right now I'm going to, so let me back up real quick. So the compiler, you can actually click this button, compile yourself. I've got it set to auto compile. So anytime I make a change to my contract, it'll compile and it'll actually show me any errors going on if there's something I've typed incorrectly. So instead of pushing this button every time, I'm just going to have it set on auto compile. So To deploy, you just come over to this deploy tab, click the deploy button, and once it does deployed, you'll see down here and the instance that it actually deployed. And we've also got buttons representing the methods that are on this contract. So if we click this button, we can see down here the contract call, and then we can actually decode the output of the contract. Bigger just in case. And we can see the address that was returned. So this is the owner. If we check up here, 0x5b3 ending in EDDC4 is the address we deployed in, so that is the owner. I guess, let me check back. Is there anybody with any questions? I don't see anybody in this chat. If there's anybody with any questions or anything, I think come to the stage and then you can actually type in any questions. If not, I'll just continue. All right, I'm gonna continue. So back, come on. Back in our code, we've already set up our owner. Next thing we want to do is find what a beneficiary looks like. So a beneficiary is going to be of type struct. So in Ethereum, you can create these structs, which kind of represent objects. It's just an easy way to organize things. So we're going to call this struct a beneficiary. Within this struct, we're going to have a bunch of a few other variables. So we're going to have an address. The address is representing the wallet of who we are basically depositing Ether for. And another keyword we're going to add to this wallet or this address is payable. And what payable means, it tells the Solidity compiler that this address should be able to receive Ether. The way Solidity bytecode works, I'm not going to go too deep into it, but the compiler builds up the bytecode in a way that kind of optimizes resources. So without adding payable to an address, if you know this address is not going to receive any Ether or do anything with Ether, it's better to leave payable out, and this actually saves up resources. And the way resources in Ethereum are spent is in the form of gas. So if you've ever seen anybody complain or talk about transaction fees for Ethereum when they're running smart contracts, this is what they're referring to. The miners for the Ethereum blockchain are all running a version of the Ethereum virtual machine. So every transaction that runs on the network has to run on every miner's machine. And so you're actually using real resources and real CPU and real memory and real network bandwidth. So to keep people from spamming the network, Ethereum charges gas. And every operation run through a smart contract charges a specific amount of gas. So the compiler for Solidity tries to optimize for this by keeping gas as low as possible. And payable actually incurs a specific amount of gas, so unless you need it, it's best to leave it out. I hope that wasn't too long-winded or confusing, but that's what payable means. The next thing we're going to have is a string, and the string is just going to reference the name of the beneficiary. Next is a uint, or unsigned integer. And this represents the time of the release. So for example, if we want this beneficiary to be able to withdraw their funds, I don't know, like 5-10 years from now, we would set this as a timestamp, a Unix timestamp in seconds, representing a time 10 years from now. uint is actually short for uint 256, which is a 256-bit integer, and unsigned integers are just integers that are positive. So you can't have negative integers with uint. But just to keep it short, we just call it uint. You can also have uint 8, uint 64, uint 16. There's various sizes of integer depending on how you want to organize things. So if you want to save on resources, you can actually specify a smaller type of uint. And the other thing we're going to add is uint for amount. Now in Solidity, another quirk is that they don't have any sort of built-in floating or decimal point numbers. So when you see actual fractions of like tokens or Ethereum, what's actually going on under the hood is, Ethereum is using really large numbers and basically doing math behind the scenes to represent decimals. So when you think of 1 ETH, actually represented under the hood is 1 with 18 zeros behind it. And basically the smallest, so you can actually represent Ether by really small amounts. Yeah, I don't know how else to explain that, but to basically simulate floating point and decimal numbers, the Solidity or the Ethereum virtual machine uses just really large integers. So to represent the amount, we're also going to use a uint 256 to be exact. And that's it for the beneficiary. So next we need to create a function to add a new beneficiary. So to create a new function, use the function keyword, and you just give it a name. And just like in any other language, you use parentheses, and we're going to give it some arguments. So we need the address. The address is payable. Wallet address, we're going to give it string name. Now, another weird thing about Ethereum is you have to, for arguments, you have to give them different keywords. I'm not going to explain too much detail here in this lesson, but we're going to give this the keyword of call data. And call data is basically a special place in memory, basically saying that we're not going to store this, or basically we want to be able to access this without actually creating a new memory location. We're just going to use the pre-allocated call data memory space to store this variable, just so we can access it quickly and store it later. I'm not going to get too much into that. And then the last thing we want is the release time. Yes, so one thing I forgot, so we've created a beneficiary, but that's just defining the struct as a type. We actually need an array of beneficiaries. So to define an array, you need to give it the type and then give it parentheses to denote it as an array. We're going to make this public so we can actually view it later. And then we're just going to call this beneficiaries. So this is where we want to store all of our, should be lowercase. This is where we're going to store all of our beneficiaries when we create them. And arrays in Solidity all inherit this method called push. So we're going to simply push a new beneficiary into that array, and then to declare a new struct in Solidity. This is the syntax you use, is basically the type of the struct, parentheses, and then you basically give each of these arguments in order, kind of like you're calling a function. So we're going to add the wallet address, name, release time, and just because we're just creating this beneficiary and we haven't deposited any Ethereum for this beneficiary, we're just going to set the amount to 0. And looks like we have some sort of error. Oh, semicolon in the wrong place. Oh, and another thing I forgot, you need to declare some sort of scope for the function. So in Solidity, you have public, private, and then some other you might not have seen in any other languages. You have external and internal. So we're going to declare this as external. This basically tells the Solidity compiler to do what it needs to do to make sure. So basically this tells us the Solidity compiler that this function is only accessed from outside of the contract. No contract, or the contract itself is not going to ever call this function. And this will tell the Solidity compiler to do what it needs to do to save resources. I could declare this as public, but this would allow us people to access it from outside, and would also allow us to access it from inside the contract, which we don't need. So it's better to just declare it as external. I hope that makes sense. I'm going to pause again, see if anybody has any questions. All right, no questions. I'm going to continue. So we've basically added this add beneficiary function to add a new beneficiary. But one problem we have with this function right now is that anybody can add a beneficiary. And before, we created this owner, which is supposed to act as kind of like an admin for this contract. We want only this owner to be able to add beneficiaries. So we need to be able to restrict this method, so only the owner can call it. And the way we do this is using a require statement. And all a require statement is basically checks a condition and reverts if this condition is not met. And all reverting is when it comes to Ethereum smart contracts is basically exiting the transaction without continuing. So nothing will so if there was any sort of state being changed, like you changed a variable or something in this transaction, all of that would basically be erased, and nothing, the state of the transaction will be the same as it was before you called the function. Yeah, so this is actually helpful because if you have any sort of errors, you don't want to have any sort of like weird bugs where you saved something to a variable and then you had an error and that variable is saved and you don't want it saved. So here, the thing we're going to check is that message.sender, meaning the person calling this function, is equal to the owner. If not, we can add a helpful message, and we're going to say only the owner can add a beneficiary. So now this basically acts as a guard to this method, allowing only the owner of this contract to call this method. So let's delete this old instance. It's already been compiled because I have auto compile. And let's deploy it. You can see it's been deployed successfully. We'll go down to this instance. Since we've created this beneficiaries array, it automatically creates a method for us to call. And for arrays, basically the method takes an index and then returns whatever data is at that index. So if we try to call this at index 0, we actually get an error because you're trying to call an index that doesn't have anything stored, which is actually good. We don't want to expect to get anything back anyway. So let's go ahead and add a beneficiary. To get a wallet address, I'm just going to go down to one of these predefined addresses, copy it, and then go back. Paste this here, call this Bob. Release time. So in order to get a release time, I've got this Unix timestamp converter, just unixtimestamp.com. And I can just put in any date. The date right now doesn't matter. So I'm just going to copy this, go back, paste that in, and then click transact. And so we got the green check mark, and we can see that it succeeded. And so if we go back to beneficiaries and we try to run this method, we should, so the call actually returns our beneficiary. So you can see that returns the wallet address, Bob, release time, and an amount of 0. So what if we tried to run this from a different wallet, not the admin? So this right here is the owner admin. If we go back and change our wallet to this and try to call let's go ahead and clear this log, try and run the same method, we get an error. And this tells us that our require statement is working. Let me ask for any questions again. No questions. I'm going to continue. So we've defined our beneficiary. We added a beneficiary. One step I forgot to add, we need to be able to deposit Ether to a specific beneficiary. So the next step is to create a new function. Call this deposit to beneficiary. Is that right? Take in an address and we're going to call this wallet address. This is going to be another external method. And it's going to be payable. So addresses can be payable and methods can be payable. So this tells the compiler that this method will take Ethereum, because we plan to actually work with the Ethereum that's being sent to the contract while calling this method. So without this, if you tried to send Ethereum as part of the transaction calling this method, it will actually revert. This is actually kind of like a safety thing. You don't want to be calling methods that aren't going to do anything with the Ethereum, because you could potentially lock this Ethereum into the contract forever. And if you calling a contract, sending Ethereum to it, and it doesn't have any way to withdraw this Ethereum or do anything with this Ethereum, that Ethereum is locked in that contract forever, and there's absolutely no way to get this Ethereum back. So this is a kind of a safety mechanism built into Solidity. So to continue, in order to, so we're going to take an address, a wallet address, and we're going to deposit the Ethereum that's actually being sent to a specific beneficiary. So the first thing we need to do is find the specific beneficiary in this beneficiaries array. And to do that, we need to loop through this beneficiaries array. And so much like other languages, Solidity has a, has a for loop. And so if you've seen a for loop before, you'll recognize this, this pattern. So for I equals to z equals 0, while I is less than beneficiaries. So arrays also have a property called length. So while it's less than the length of the array, and then for every at the end of every iteration, we want to increment I. So we've got I representing the index of this array, and we want to check if beneficiaries with the index of I, check if the wallet address is equal to the wallet address we specified in this argument is the same. And if it is, we want to set that particular beneficiary's amount to, or we want to add. So basically, we want this function to work multiple times. So for example, if we send 1 ETH the first time, it's going to add 1 ETH to the amount. If we send 2 ETH the next time, we want to basically the amount to be 1 plus 2, which will be equal to 3. So we don't want to overwrite the amount. We want to basically add to the amount. So you can use this plus equals operator, which is also the same as equals beneficiaries index of I dot amount plus whatever. But we're going to use this shorthand. Other languages have this shorthand too, so it should be pretty recognizable. So it's going to be plus equals message dot value. And message dot value, again, is one of these global variables representing the amount of ether sent to the contract. Basically, it's the amount of way. I'll explain way here in a little bit. But basically, we want to append or add this value to the amount. And yeah, that should do it for this method. So Oh, and another thing, when you send the ether along with calling this function, the balance for this contract will automatically be updated. So there's really nothing you have to do. The ether will automatically get stored in the contract. We just want to denote that this particular ether being sent with this contract belongs to this specific beneficiary. So this is already saved. Let's delete this and deploy a new instance. So we have this instance. We're going to go back to our owner address. We're going to add a new, all right, let me copy this address again. Because this is a new instance of the contract, all the state is basically zeroed out. So we have to add this beneficiary again. So we're going to add this beneficiary, Bob. We'll just copy this timestamp. Oh, I have to go. I messed up. So let's delete this instance. Because I deployed it with the old address, which was this address, that was the new owner of that contract. Just to keep things clear, we're just going to go back to the first, deploy one more time, open this up. I should have that pasted. Okay, cool. Bob, copy this timestamp again. Transact, all right, everything works. If we check the beneficiary, it should exist. So if you see down decoded output, yep, we've got our beneficiary. And so now we want to deposit to this beneficiary. So just copy this address. Paste it here. And in order to send an amount of ether, we have to go up here. And so this is asking for an amount in Wei. Wei represents the smallest unit of Ethereum. So remember how I told you that amounts of Ethereum are represented by whole numbers, really big whole numbers with a bunch of zeros at the end. So Wei would be, so one Wei would actually be 1 to the times 10 to the negative 18, something like that. So if you wanted 1 ETH, this is what it would look like in Wei. By the way, if you want a useful converter with a bunch of other tools helping you develop in Solidity, check out tools.deth.net or deth.net. It's got this handy converter. So one Wei would actually look like this in Ethereum. So we're going to send just 1 ETH to the contract, and this is what it's going to look like in Wei. So instead, we're just going to use the Ether dropdown, send 1, and go back here to transact, and hopefully that worked. Looks like it worked. And so what we can do now is check this beneficiary again. You can also see the data down here that's returned. And you can see that the amount returned is 1 with a bunch of zeros. That doesn't mean you have like a bazillion ETH. It just means you have this much represented in way, and this actually equals 1 ETH. All right, I'm going to pause again to see if there's any questions. Okay, I see one question. How do you decide when to use public? So public is when you want other people to be able to access the method from outside of the contract. You can also have private functions which are only accessible from within the contract. So for example, you would have a function that basically for the sake of clean code, you have like some really crazy complex operation. You can push that code, put that code into another function and make that private because you know it's going to be called from another function within your contract. I hope that makes sense. Any other questions? All right, let's continue. So next, just to show you that this contract can have a balance to it of Ethereum, we're going to create a function that will show us the balance of this. So we're just going to create a function called contract balance. It's not going to take any arguments. Like I said, we can make this public, but public means you can access it from outside. You can also access it from inside the contract. We don't care about using this inside of our contract, so we're going to use external. And another keyword we're going to add here is view. And I'm going to explain that here in a little bit. So this function also is going to return a variable. So any function that returns something, you have to tell the compiler what it's actually returning and that in parentheses. So we're going to return a uint, which is the value held by our contract. And this is going to be a one-liner, essentially. So I'm just going to type this out and then just kind of explain what this all means. So to represent the actual contract we're talking about, which is this contract, we use the keyword this. And then because we want to use this balance property, which only exists on a variable of type address, we need to typecast this contract as an address. So we can do this by just using the address keyword, parentheses, and then enclosing this in parentheses. And this gives us access to the balance property. And then we're just going to return it. There's nothing fancy we need to do. This will automatically know what the balance of the contract is and return it. And so this takes us back to this view keyword. The view keyword tells the compiler that we aren't actually performing any other operations. We're simply reading state and returning state. We're not actually saving to any state. We're not actually manipulating any state. So in order to save resources, we can tell the compiler, hey, this is only a view method, and do what you need to do to optimize this way. So that's what that view method means. So let's go ahead and get rid of this old instance, deploy this again. We're gonna have to go through all the steps again. So it's deployed. We have to add a beneficiary. Bob, release time. And let's go ahead and give Bob some ether. I need that address again. Send him 1 ether. All right, that worked. And so now we have this contract balance method that we can call. If we call it, we can see that we have, well, I'm going to say a bazillion way, but 1 ether. And if we do this deposit to beneficiary again, we can see that the balance actually changes. So let's give him 2 more ether just to be generous. If we call the contract balance, we can see we have essentially 3 ether as the total contract balance. I'm going to pause for questions again. I don't see any. So let's continue. So we've got next to basically allow the user to check whether they can actually withdraw their balance. So one thing, yeah, so to start, create a new function, call it available to draw. Take an address as the argument again. This is going to be public because I want to use this in another function later, and you'll see. It's going to be view because it's not going to manipulate any state, and it's going to return a bool or boolean, true or false. So one thing we need to do is I want to iterate over our beneficiaries again to see if this wallet address matches. And because we did this here and we're going to do this again here, I'm going to create a utility function to help us do that and kind of clean up our code. So we're going to create another function down here, get index, and this is going to search using an address through our beneficiaries array and then return the corresponding index. So this is going to take a wallet address as well. This is going to be private because nobody needs to use this outside of our contract. Also going to be view because it just doesn't manipulate any state. And it's going to return a uint, which is the index. It's also going to return a boolean. So in Solidity, you can have functions that return multiple values, which can come in handy sometimes. And it's very similar to Go, if you've ever used the Go language. And so basically, this first variable is going to be the index, and this boolean is going to be whether or not this index actually exists. So if the index doesn't exist, it's going to return false. So So I'm going to basically do a copy and paste here, just for the sake of time. So we're going to loop over the array, check to see if the address matches, return the index, and then also return true. If not, we're going to return something a little different and false. So here, I'm returning a very interesting value. Basically, I'm returning the largest possible value a unit can hold, which is a very large number that realistically you will never reach as an index to an array. I mean, you'll run out of resources that way, and you'll never have this many beneficiaries. It's pretty safe to say this. And the way to get the max integer or unsigned integer is to use this type keyword, parentheses, the type, which is uint, and then this max property. So return that's basically to say, yeah, this index is not referencing anything. We also return false, saying that basically we didn't find the address you're looking for. So now we can go back to this. So because we have this this new utility function, we can actually refactor this deposit to beneficiary function here. And I'm just going to one second. I'm going to copy paste to save some time. So here we've refactored. So instead of doing the loop like we did before, we just use the utility function to get our index and also check if it's okay. If it's not okay, we just return end the function. One thing I think I should actually do is revert. So we're going to require okay to be true. If not, give a helpful error, basically. So this will actually prevent ETH from being locked in the contract. Before, what I had before, what I just noticed, it would actually, the function wouldn't actually fail. It would just return, and then you would actually still send the ETH to the contract, and it would be locked there. This will actually revert. Any ETH sent to the contract will be sent back. Yeah. And if it is okay, we actually update the value like before. And so we can do the same here. The index, and if the index actually exists, the next thing we want to do is check that the timestamp on the beneficiary record is greater than the, we want to check that the current timestamp is greater than the timestamp or the release time that we set for the beneficiary. So we can do this by checking block.timestamp, which is a built-in global variable, part of that cheat sheet that I showed you before. We want to check that it is greater than, or that, in other words, it is later than the release time of the beneficiary. So we can access that. The beneficiaries, using index and then release time. So if it is greater than that, we can return true. Otherwise, we can return false. So this tells us whether or not we can withdraw. I'm going to pause again. Any questions? No questions? So, yes. I don't see any questions in the chat, or do you have a question that somebody's asking? Let me check. Oh yeah, I answered that question already. All right. Let's continue. Let's see. So the next step, because now that we can check whether we can withdraw, we want to be able to withdraw. So I'm going to add one more function. And I'm going to take an address, wallet address. This is also going to be external. And so we're going to use this utility function below again to get the index. And basically make sure that this beneficiary exists. And then we're going, now that we have the index, and we're going to do a bunch of stuff with this beneficiary, we're going to basically store it in memory, just so we don't have to type, do longhand typing of the array with an index. So we're just going to grab beneficiaries with that index stored in this variable b. And then the first thing we're going to do, we need to make sure that whoever is calling this needs to be the actual beneficiary. So we're going to use a require statement, and we're going to require that the message.sender, remember that is equal to whoever is calling this method, is equal to the wallet address of the beneficiary we're working with. I'm going to give it an error message if it's false. And one other thing we need to check is whether or not we are able to withdraw. And so the reason I made this public instead of external is I can actually use this from within the contract. So I can just use available to withdraw the wallet address of our beneficiary. If this is false, let's say not able to withdraw. And so to get prepared to withdraw the Ethereum, we're going to set the amount to 0. I'm basically doing some accounting And then we are going to take the wallet address, and every payable wallet address in Solidity has a built-in method attached to it called transfer. And so we are going to transfer I set this to 0. All right, so this is going to look a little bit silly at first, but I'm going to tell you why I'm doing this. So I created a new variable called amount, set it to the amount of b.amount, and then I'm going to set b.amount to 0. So now I can transfer this amount, and this will transfer that amount of ether from the contract to this address. So the reason I do this is it's just a best practice to get into. There's something called a reentrancy attack in Ethereum. So before you transfer any type of tokens or ether in a method, if something is supposed to be set to 0 or decremented or changed at the end of the function, you want to do all of those things before sending any of these tokens. I mean, this particular function is not susceptible to reentrancy, but all reentrancy is because you can actually call functions from within functions. If this function had the ability for a user to, I guess, call this contract again from this function, basically all they would have to do is create some sort of loop where they could continuously call this function and transfer this amount of ether out multiple times before actually failing. And this would allow them to basically drain the contract without any sort of check that their balance is 0. So we basically want to make sure that their balance is set to 0 before any sort of sending is done as kind of a best practice. And so that's why I do this. Honestly, I could have just said send b.amount and then set the address or amount to 0, and this would have worked just fine. I just wanted to kind of like instill a best practice. Hope that makes any sense. Are there any questions about that? I see a question. Oh, okay. I will introduce myself again at the end of this. All right. Let's continue. So yes, this should allow us to withdraw, and everything looks good. I'm going to clear out the logs and clear out this instance and deploy one more time. So next step is to copy this address. We're going to add our beneficiary. Call it Alice this time. And we're going to create I'm going to refresh this basically, because we want to be able to withdraw. So I'm just going to copy a timestamp of now, essentially, and create the beneficiary. We need to deposit some ether to that beneficiary. And so we can check that beneficiary, see that they have 1 ETH. We can also check to see if it's available to withdraw. It's true because I basically put in a timestamp of a few seconds ago. And so we can actually try to withdraw. It should give us an error because we're withdrawing from a different address. Yes, so it gave us an error. If we switch to the address of that beneficiary and try to withdraw, it worked. I don't know if it actually tells you if something had been transferred. No, it doesn't actually tell you, but and I'm not sure how to demonstrate that. Yeah, so we were at like 99 something ETH before. You can see we're up to 100. So the ETH did get transferred to this beneficiary. And we can also check the balance of this beneficiary is back down to 0. So everything worked. Before going into the last few parts, the extra parts, I'm going to pause to see if anybody has any questions. No questions. All right. So hopefully all of that made sense. Next thing I'm going to talk about is events. So most people are not going to be interacting with these smart contracts directly or through something like Remix, like a developer would. Most people are going to be interacting through some sort of user interface. So a UI in a website or web app is going to have like some nice fancy inputs and buttons and stuff like this to talk to the contract. And one way to get information about the state of the contract or what's going on in the contract is to use some of these methods like the contract balance method, or you can build in some other methods to give information. But another way to give information about what's going on with the contract is what's called an event. An event is just like you can kind of think of it as free almost storage for the contract, because it doesn't actually store anything in the contract itself, but it is emitted as kind of a log. So all of the different miners, clients, and indexing services for the blockchain actually read these logs and store the logs on their servers, so you can actually read stuff that's happening. And to create an event in Solidity, you just use the event keyword, and then you just give it a name. So let's create an event called Beneficiary Added, and it takes a bunch of arguments. So basically we're going to, so we want to log the address of the beneficiary and the name of the beneficiary. You can log whatever you want. This, just for demonstration's sake, we're going to just keep it very simple. So we've got this event, and we want to log every time we add a new beneficiary. So to log this, you use the emit keyword, the name of the event beneficiary added, and we can just pass in the wallet address that we added as one of the arguments and the name. So this should work. Let's deploy this. And I hope we're just going to add ourselves as a beneficiary. It doesn't really matter. Let's give random number. And so if we go down to inspect this, I'm hoping it gives us a breakdown of events. Yes, so events are shown as logs in Remix. So we've got this log, and you can see the event beneficiary added, and then these are the arguments emitted by the event. So this is useful so UIs can actually listen to events on the blockchain and basically react in real time to what's going on the blockchain. So you don't have to constantly, query the contract for state. You can just kind of sit there and listen for events as they happen. Any questions about events? All right, and then the last thing I want to go over is modifiers. And modifiers are kind of a way to clean up your code and make certain aspects reusable. So we have this require statement right here that only owner can use this function. But what we can do up here is create what is called a modifier. And we're going to call it only owner. What a modifier does is it's kind of like adding little small bits of functionality or checks to your method. So we can remove this, add this here, and then at the bottom, add this little underscore. Basically, let me add this to our add beneficiary function real quick and explain. So we've added this only owner modifier to add beneficiary. And what this means is while you're running this method, we want to run this check and revert if this check is false. And this right here, you can kind of think of it as a placeholder for the logic within this add beneficiary method. So before running anything inside of this, which is represented by this placeholder, we want to run this check. So we can add this only owner also to other methods without having to write this over and over. So for example, if we want to limit deposit to beneficiary to only allow the owner to do it, we can add the owner as well. So we can check to make sure this works by deploying. So the owner is this 0xab8 address, and then we can go over here, try to add a beneficiary. Try to add it, and we get an error, and it should actually tell us why. Maybe it doesn't. Yeah, maybe Remix doesn't actually show us. No, oh, actually the message is right here. Only owner can add a beneficiary. So this works for any method now rather than having to type in this ridiculously long require statement for every function you want. And that is essentially it. Any other questions? All right, I guess I'll go to the general area and anyone can just kind of come chat with me. Thanks everyone for watching. Yeah, if anyone wants to ask me anything, I'm open for any questions.
Hey Ed, can you hear me?
Yes, I can hear you. Go ahead. I can't hear you now.
Yeah, so I just wanted to thank you. This was super great.
Oh, no problem. My pleasure. My very first live stream, so I was a bit nervous, but it seemed to go okay.
Yeah, well, I couldn't tell that.
Thank you. Appreciate it. Oh, I see a question. Someone wants me to explain again the reentrancy attack. So reentrancy. So you can have. It's kind of difficult to explain, but if I had a lot more time, or maybe in a future stream, you can have contracts that can call other contracts, or contracts that can actually call themselves. So very complex applications or DeFi protocols and stuff like that. It's actually just a bunch of smaller contracts talking to each other. So you can have a method or function that does one thing and maybe calls another contract after sending some tokens or before sending some tokens. And it might not actually check that the contract it's calling is doing something malicious. So what can happen, say for example, there's a contract that everybody has a bunch of balances stored in this contract. So it's just a record of an address and then how many tokens that this address holds. And so in our example, we have this withdraw function. And so say this withdraw function does a bunch of stuff and actually sends the amount that the address holds to the address. But after it sends this, it can call another contract to do something. It doesn't really matter what. So an attacker, so if we didn't actually set the address or the balance of that address to 0 before sending these tokens to that user, if they were able to specify a malicious contract to call before this function ends, basically this function can call back to this method to basically withdraw again. And because that balance is still the same, it hasn't been zeroed out, it'll send more ETH over and over and over and over, because you can just do recursive calls over and over, basically until the contract. And then that's essentially how someone can steal a bunch of ether. I'm not sure if that makes sense. It's very hard to illustrate or wrap your mind around, but essentially it's a way for people to loop, to drain a contract without actually having the balance that the contract says they have. Let me know if that makes sense to you. I'm guessing yes. I see another question. It says, could you explain how you created and I don't see the rest. Let's ask that question again or retype that. I'll be happy to answer it.